Swayam Prabha. Digital India. Educated India.
So let's come back to the important question, what is program analysis? Okay, so program analysis involves discovering information about a given program, which must represent the dynamic behavior of the program. We are interested in the runtime behavior of the program. But most often this information is obtained without executing the program. I mean, there are dynamic analyses which run the program and compute this information while executing the program, but such analyses and such optimizations are not very common because they have to be lightweight, because they add to the execution time of the program. So in most cases, program analysis means static analysis, although please note that there are dynamic analyses as well. Here we are going to focus on static analysis. So this is the story. The story is we want to find out the runtime information, but we don't want to run the program. We want to merely look at the program, stare at the program, analyze the program, and find out what could it possibly do at runtime. Okay. The important requirement is, and this is the most important requirement, it must represent all execution instances of the program. If we miss out certain execution instances, then the information that we compute is unsound. For soundness of analysis, we require that, because we are doing it at compile time, we require that every execution instance of the program must be covered. Why is it useful? So it is used for code optimization. For example, it's used for improving time efficiency, space efficiency, energy efficiency, or power efficiency. It is used for compilation of special architectural features, for example, compilation for multi-core. It is used for verification and validation. For example, it can be used for giving guarantees such as the program will never divide a number by 0. There is no zero divide exception. The program will never dereference a null pointer. The program will close all opened files, all open socket connections, and the program will not allow buffer overflow security violations. So these are some examples. There can be many more such requirements of verification and validation. It may also be used for software engineering, for example, for maintenance, bug fixes, enhancements, migration, etc., code migration. It may also be used for reverse engineering to understand the program. Okay, so important requirements of static analysis are soundness, precision, efficiency, and scalability. Soundness and precision, we are not going to cover here. I'm sorry, I should have modified this slide. These slides are from my course. We will not be able to look at soundness and precision in great details formally as a part of this tutorial. But we want to talk about soundness, precision, efficiency, and scalability. So the important thing is static analysis results are inexact. They predict runtime behavior of the program, and in general, static analysis is undecidable. And undecidability here means that there cannot exist an algorithm that can cover exact result for every program. This is simply because we do not know whether the program will ever terminate. We do not know exactly which execution paths will be taken by the program. So we have to over approximate. It's possible that a certain condition is false always, but in general, we may not be able to discover that a certain condition is false always in every possible run. And it is in this sense that static analysis is inexact. It cannot give us the exact behavior of runtime behavior of programs. This problem, the finding out the exact runtime behavior of programs, is undecidable. And because the problem is undecidable, we have to think of certain approximations. And why is the problem undecidable? Because the values of variables may not be known at compile time, and therefore branch outcomes may not be known at compile time. There may be infinitely many paths in the presence of loops or recursion. So there are infinitely many execution instances, potentially infinitely many execution instances. There are infinitely many values, and therefore we may not be able to pinpoint exactly and say that this is exactly what this program does. So what we do is we try to over approximate. We try to find out the behavior which covers in some sense every possible execution in a sound manner. Besides, some features are very hard to analyze at compile time. For example, let's think of eval in JavaScript, or aliasing of array indices, or the effect of libraries, etc. So we have to somehow overcome these unknowns, and therefore we cannot give exact results, but still we have to give certain guarantees. Okay, so what does this slide say? This slide essentially says that static analysis predictions may not match the actual runtime behavior. And if they do not match that, if there's no guarantee that they will match the actual runtime behavior, what good things can we say? And this is where we have to talk about possible errors and categorize the errors. Okay. Some predictions may be erroneous because the predicted behavior may not be found in some execution instances, or they may not be found in any execution instance. And by error, we are essentially meaning here the mismatch between runtime behavior and predicted behavior. So there is a certain predicted behavior and there is actual behavior. So is there a mismatch between actual and prediction? If yes, there is an error. Okay. Now, the interesting thing is some of these errors may be harmless, whereas some may be harmful. And this distinction is very, very important. Okay. Some of these errors may also be unavoidable because of undecidability. Okay. So how do we characterize, detect, and minimize these errors? We can't simply say static analysis may have errors. And if that's the case, we will use static analysis. And how do we know that the optimization that we are doing will not change the behavior of the program in a harmful way? So we need to characterize, detect, and minimize these errors. So we divide the errors into possible harmless and harmful errors. So error, once again, is a guess leading to an action which is different from the actual reality. Okay, so let's look at some intuitive examples. A security check at an airport. Let's take that example of security check at an airport. So if you frisk a person more than others on mere suspicion, that is harmless from the viewpoint of security. Okay. But if you do not frisk a person even after suspicion, then it could be harmful. Okay. So for stopping smuggling of contraband goods, not checking every passenger is harmless, but checking every passenger is harmful because it will cause delays. Okay, because security is different from smuggling. Weather prediction during rainy season. A doubtful prediction of heavy to very heavy rain is harmless. But if you're not sure whether it will rain from heavy to very heavy, and if you do not make that prediction, then people will be careless and this could turn out to be harmful. Okay. So further examples of harmless and harmful errors. For medical diagnosis, for example, in the era of COVID, and you suspect that you have certain symptoms of COVID. Okay, so subjecting a person to further investigation, going for COVID test is harmless. Okay, it's not going to add to your misery. But if you didn't go for COVID test, then it could be harmful. It could turn out to be something very bad for you. On the other hand, establishing justice in criminal courts, starting with the assumption that accused innocent is harmless, and that's why the courts begin with that. Starting with the assumption that an accused is guilty could be harmful because you could end up penalizing someone who is actually innocent. Okay, so these are some examples of harmless and harmful errors. Okay, and admittedly, this situation is quite confusing, where what is harmless, what is harmful, we will define that precisely as we go along. But for static analysis, harmless errors can be tolerated but should be minimized. The whole purpose of previous discussion is not to define what is harmless and harmful, but to show that we can make distinctions between harmless and harmful errors. Okay, so static analysis can tolerate harmless errors, but they should be minimized. This talks about precision of analysis. The fewer harmless errors you have, the more precise analysis you have. The more harmless errors you have, the more imprecise analysis you have. Similarly, harmful errors must be avoided. This deals with soundness. If you have any harmful error, if your static analysis admits any harmful error, then the analysis is unsound. So it must avoid harmful errors at any point of time. And this is the meaning of saying that a static analysis must be sound and it must be precise. Okay, now talking about efficiency and scalability, often people confuse between them. They think that everything that is efficient is scalable and everything that is scalable is efficient. But no, they are, in general, they could go hand in hand for many cases, but they could be different. They are essentially orthogonal. Efficiency deals with how well resources are used. It's measured in terms of work done per unit resource. And here the resources could be time, memory, power, energy, processors, network, number of processors, network bandwidth, etc. Scalability deals with how large inputs can be handled, and it's measured in terms of the size of the input that can be handled and not the time required to handle that input. So example of efficiency is strike rate of a batter in cricket. And whereas example of scalability is total runs scored by a batter in cricket. For example, yesterday, if you have watched the India versus England women's cricket, you would find that Shefali Verma was not only most efficient, but she also scored more runs than anyone else. Her strike rate is much higher than Mithali Raj, but Mithali Raj has scored many more runs. So that's the difference between efficiency and scalability. Okay, efficiency and scalability are orthogonal. Efficiency does not necessarily imply scalability, and scalability does not imply efficiency necessarily. I'm going to not discuss this any further, but I'm going to leave this slide with you for you to think about. So merge sort is an example of a scalable and efficient sort. Selection sort is an example of scalable but inefficient sort. Quick sort is efficient but non-scalable, and bubble sort is both inefficient and non-scalable. So you do a bit of exercise and figure out why this is so, and that will tell you why efficiency and scalability must be considered as two distinct things. So coming back to the most important question, what is static analysis of programs? So static analysis involves building suitable abstractions for sound and precise modeling of runtime behavior of programs efficiently. I haven't put the word scalability here, but I think I should put it here. Each and every adjective used here in the blue font is very important. First of all, we have to build abstractions. We can't be dealing with actual programs. We have to throw away a lot of information and focus on the information that is useful to us. So we have to build abstractions. Second, these abstractions have to be suitable for the purpose that we have in mind. And then these abstractions should help us model the program in a sound manner and in a precise manner. The modeling should be precise. There should be as few harmless errors as possible, and there should be no harmful error. And this models the runtime behavior of the programs, and all this process must be efficient and scalable. So What we have here is we have a static world and we have a dynamic world. In the static world, we have program code. And in the dynamic world, we have program in execution, which is a process. So for a single program code, there could be multiple processes that are possible. Program code is abstract, bounded. There is a single instance of a program code, whereas a process is concrete. Program is abstract because I don't know the value of variable X. The process is concrete because I know the value of variable X. Program code is bounded because it is finite in size. Process is unbounded because I don't know how long it will go. And for a program code, there is a single instance of program code, but there could be infinitely many different processes for a particular program. And each of these processes could lead to memories that are concrete, unbounded, and infinitely many. And what we want in the static analysis is we want to take the summary information of what's happening to the memory, what's happening with the data, with the data of our program. However, we do not want to take this long route of going from static world into dynamic world, running the program and then examining the memory and then computing the summary information. This is done by profiling, or this is done by what is called feedback directed compilation. But in static analysis, we do not do that. In static analysis, what we wish to do is to remain within the static world, and we want to say we don't want to look at this part at all. Our focus has to be on this particular box. Our focus has to be on program code and summary information. The important observation here is summary information for a program must be a function of the program. It cannot be not a function of a program. And therefore, static analysis tries to infer this function. Static analysis tries to say, give me a program and I'll try to give you the summary information. This is the purpose of static analysis. Okay, so with that, we come to the end of the first hour of the lecture. And before we talk about variable analysis, I will be happy to take lectures. I will be happy to take questions, I'm sorry. Any questions about what we have seen so far?
Sir, could you please elaborate on the last part that you just mentioned about the static, that we should be bothered about the static portion of, yes, sir, this one. I couldn't get it exactly, sir, what we meant by that.
So what we're trying to say is the following. We want to find, so let's take this example. We want to find out which assignments are dead in a program. Okay. So therefore, we want to find out at every program point, which variables are used or likely to be used after that program point. Right? One way of doing that is to run that program multiple times and see, observe which variables are used for beyond every program point. That's one way. The other way is, let's not execute the program. Let's remain in the static world. Let's just stare at the program code and try to infer from it what is likely to happen. Right? So, yes. Which means that we do not want to run the program. We want to build a model of the runtime of the program without running the program. And this is what makes static analysis very, very interesting. We try to look at program semantics, map them to the static world, and then develop mathematics that will manipulate that program semantics, which will help us discover summary information, which we can transport back to the dynamic world and be sure that the changes that you're doing in the program are absolutely fine. They will not affect any runtime behavior adversely. So the idea is to remain in the static world.
Right. So that means we are not bothered about the executional part of it. We are only bothered about how it is behaving currently when we are not running it on a platform. That's what we mean to say, sir.
Actually, no. We are very much bothered about the executional aspects, except that we want to do it without executing the program.
Sir, got it, sir. Yes, sir, got it, sir.
Yeah. I mean, everything is about program execution. But what makes it very interesting is we don't want to really execute it. We want to imagine what executions could happen. We want to imagine what could happen in those executions, and then we build interesting abstractions, and then we build interesting theory around it, saying that okay, this is our abstraction. So just let's take a concrete example of live variables analysis. How did we look at the informal introduction of live variables analysis? We said here is the statement. After this statement, we know which variables are live. We didn't ask a question, how did we arrive at it? We will find out a way of arriving at it. Then we said, if we know which are the variables live here after the statement, can we look at the statement and infer which variables will be live before the statement? Right? So the set of live variables is an abstraction of runtime behavior of the program. This abstraction represents that from this program point onwards, these are the variables that are likely to be used. This is an abstraction because we have thrown away every other information of the program. We're simply keeping track of which variables are used after this program. So this is something that we do, and we look at a statement and then we say what is live before it. This is how we compute it. Now the question is, how did we get the set of live variables after a statement? Because then the answer would be that it would we would get it by looking at the statement after this particular statement. It's the same story of turtles all the way around. The earth is standing on a turtle, and that turtle is standing on some other turtle, and that turtle is standing on some other turtle. But unlike the mythology of turtles all the way around, our program is finite. So we have one statement, we have then a statement after it, then we have a statement after it. Sometime we want to come to the end of the program, right? And then at that point, we know that nothing is live. So now we have a case where we concretely know that nothing is live. From there, we infer something before that statement. We take that information, we use it to infer something before that statement. We are not executing the program at all.